present the screen. 25 on the talk and 5 on the questions, discussion.
Okay. So now it is not 10, but 10
yes,
four.
Yes. Plus
4 past.
2.
Good morning. First of all, I would like to thank organizers and personally Dim Kazakov for inviting me here to give this talk. And of course, I would like also to start with congratulations to the those who passed through 70 years jubilee, those who are here and those who are online, not on Zoom. This talk is based on a paper with Ioseph Buchbinder from Tomsk and Nikita Zagraev from Dubna. And it is first example actually of applying the harmonic superspace approach to the problems of high spins. But I start with what's me? Doesn't work. Okay. Okay. Press with some power. Yeah. So I start with giving outline. I will start with recording some basic facts about supersymmetry and high spins. In this context, then we'll give a brief account of N=2 harmonic superspace formalism. Then we'll discuss in some details linearized N=2 supergravity, which is just N=2 supersymmetric free spin 2 model. Then we'll describe, we'll pass to spin 3 model, and then finally discuss the general case of integer spin S. Until now, we could describe in this way only integer spins, not half integers. I mean, high spin in the super multiplet. And we'll finish by summary and giving some problems for further study. So, supersymmetry high spins. No, it is known more or less to the audience that supersymmetry is a very interesting and promising concept, which has a lot of achievements, namely using it such theories as supergravity, superstrings, N=4 super-Yang-Mills theory, first example of ultraviolet finite quantum field theory were constructed, etc. And using it, many new concepts were discovered. For instance, this famous IPhT correspondence. During this last decades, also supersymmetric high-spin series were intensively developed. And why it is interesting to work out this kind of series is that both this theory include in principle infinite sets of spins like superstring series. So it is expected that there exists some very deep, profound relationship between superstring theory and high spin series, and actually high spin theory can serve as a kind of bridge between superstring theory and its low energy limits, different limits. It is also known that now well known that the most natural way to deal with supersymmetric field series is just superfield approach. There might be more accustomed component approach actually yields on-shell multiplets such that corresponding supersymmetry algebra is open on them, and finding some invariant actions even free is very complicated work. On the other hand, in the superfield approach, supersymmetry closed from the very beginning. All supermultiplets are off shell, and the correct number of auxiliary fields automatically appear in the decomposition over Grassmann variables of these fields. And actually, most preferable are just unconstrained superfield formulations in terms of superfields which have some extra constraints, so defined on some invariant subspaces of original superspaces. What concerns supersymmetric high-spin models? In the bosonic case, actually massless bosonic and fermionic high-spin field series without any supersymmetry were discovered by Fronsdal, and fermionic case was considered in Fenk and Fronsdal many years ago. What concerns component approach to the to n=1 simplest supersymmetric extension of this theory, it was initiated in paper by Cartwright, Tom Cartwright, and Misha Vasilyev, also approximately at the same time. Actually, then complete Lagrangian formulation of free high-spin models and n=1 models in 4 dimensions, also include, and also the generalization to ADS background was given in a series of works by Sergei Kuzenko with collaborators in the beginning of 90s of the past century. But interesting that until present, off-shell superfield Lagrangian formulation for extended high-spin supersymmetric series, for n=2 extension of the Fronsdal theory, were not known. But it is interesting to have such extension where all supersymmetries are manifest, etc. This formulation were known even for the free n=2 series. And this gap was filled in our recent paper with Ioseph Buchbinder and Nikita Zagraev. And in this paper, we have given n=2 supersymmetric superfield formulation of n=2 extension of the Fronsdal theory for high spins for the first time. And the basic tool in this construction was the harmonic superspace approach. But what is the harmonic superspace approach is? At present, exists for all standard series with spins not higher than 2. Of course, exists for an n=1 case. It is just well known. But what concerns extended supersymmetries, they until at present they are known only for n=2, n=3 supersymmetric field series, and these formulations are based on the harmonic superspace approach developed in 1944 in our paper with Sasha Galperin, Stelian Kalitsyn, Viktor Agivetsky, and Emil Sakachev. And using this approach, it was possible to find, to construct super Yang-Mills series, supergravity series of shell, and also maybe more important to present first known of shell formulation of the basic meta-multiplet of n=2 supersymmetry, so-called hypermultiplet. And this paper, our new paper, on which my talk is based, it just opens a new domain of application of the harmonic superspace approach, just in n=2 high-spin gauge series. And firstly, I recall some basic facts about n=2 harmonic formalism. Standard n=2 superspace is the following manifold. containing Minkowski space coordinates and 8 Grassmann variables, where this alpha and Lorentz spinor Lorentz indices and I and J are from the indices of fundamental representation of aptomorphism SU2 group of N=2 superalgebra. A harmonic N=2 superspace is just extension of this guy by some harmonics, just parameters of the cassette SU2 over U1. And why such a extension is important is that in this, if you go to so-called in this extended superspace, it's called analytic basis by projecting original Grassmann coordinates on harmonics U plus minus I and shifting X, like in, for instance, an equal one chiral superspace. You find that there exists some subspace in this extended superspace, which is closed under the N=2 superalgebra. It's some analog of N=1 superspace in chiral superspace, and in the case of N=1 supersymmetry. I wrote here this transformation under which this subspace is closed. Harmonics are not transformed, only X and θs are transformed, but you see that variation of X and θs explicitly contain harmonics. So it is only this, the whole extended manifold is closed under these transformations. And it turned out that all basic superfields, N=2 super gauge series, admit description in terms of analytic N=2 superfields. These are just, excuse me. I don't know what happened. Summer. I don't understand what happens. Why is the started? Я понимаю. So we have this V++, basic object of N=2 superior Mills theory, basic objects of matter are hypermultiplet superfields, and supergravity is described in terms of this analytic superfields, having this vector indices and some additional 5 indexes in Lorentz invariant, and some superfield having spinor indices. Now, what concerns N=2 gauge theory, it is just described by a V++ superfield, which has the following gauge transformation. And using this gauge symmetry, you can go to the Wess-Zumina gauge, which includes just complex scalar field, vector gauge field, gaugina, and triplet of scalar auxiliary fields. And this multiplet just constitute abelian gauge N=2 of shell multiplet, 8 plus 8 degrees of freedom. Okay. But to construct the invariant action, we need to define second non-analytic gauge connection, V minus minus, which related to original V++ by this harmonic flatness condition. And using this condition, actually, it can be shown that V minus minus can be fully expressed through original V++. And the action has some very simple form. It's just product of two connections. It is, of course, it is not gauge invariant in itself, but it's a gauge invariant under up to total derivative. So in this sense, it's similar to Chern-Simon section in some sense. And find the component form of the section, we need to express V minus minus through V++ in Wess-Zumina gauge, then integrate over Grassmann and harmonic variables and get standard component action. Of course, it can be easily generalized to the non-abelian case. Consider this abelian case, but non-abelian case also treat analogous. What concerns n equal to Einstein supergravity? In this case, we need to extend this superspace by 5 coordinates, define the following flat harmonic derivatives, and define a group of n equal to Einstein supergravity as a group of analytic diffeomorphisms of this extended analytic subspace, xm, theta plus, theta bar plus, and x phi. This non-analytic coordinate has no transformation, but this additional gauge parameters can be fully fixed by choosing some supersymmetric gauge. And then, in order to have covariant spinor derivative, you need to introduce some Wilbeans, analytic Wilbeans, and some its negatively charged analogs given here. And from this condition, you immediately find some equations related, analogous like in n equal to Young-Mills. You get some relations between H minus minus and H plus pluses. And a linearized form of gauge transformation of basic analytic prepotentials is given here. Actually, we will need just the linearized form of this transformation for describing free spin 2 in our case. And we can, like in Young-Mills, you can choose West-German gauge, where you have just basic set is just gauge fields, graviton, gravitina, and graviphoton, so-called additional vector bosonic fields. They form just irreducible on-shell n equal to Einstein supergravity multiplet. But of course, you have additional fields which are just auxiliary fields in this case, and some residual gauge transformations, which is just diffeomorphism, 4-dimensional diffeomorphism. This transformation just gauge transformation of graviphoton, and additional local Lorentz rotation you have, and local, of course, local spinor supersymmetries. And using this additional transformation, you can put graviton into the standard form, where you have irreducible so-called conformal graviton with symmetrized with respect to all indices, spinor pointed and without points, without dots, and phi, which is just trace of the graviton. And on these fields, at the linearized level, you have the following transformations for phi, and of course for C, which is just vector field, shifted abelian vector gauge fields, which shifted by gradient of this parameter B. Next offshore action, I will discuss only linearized level. So we will need linearized form of these gauge transformations. And the basic points are following. The point is that this H plus M, H plus plus, under rigid n equal to supersymmetry have non-trivial transformation law. Namely, this guy transforms through spinor analytic superfields, and the same for H plus plus phi. And the first step is to define a new n equal to superfield, construct from this analytic ones, such that they will be invariant under rigid n equal to supersymmetry. These superfields are a singlet of n equal to global supersymmetry. But under supergauge transformation, they also have a rather simple transformation law. Difference is that from the original analytic potentials, it's just this gauge function includes also some mixture of negatively charged coordinates. These guys are analytic, but you have also theta minus and theta bar minus here. And this object satisfies the harmonic flatness condition, which is a consequence of original gauge flatness condition.
So the law of transformation for H ++.
Yes.
The law of transformation for H mu depends on H ++5. No, it doesn't depend on H ++5. So why do you need this H ++5? It seems to be closed even without that. The laws of transformation.
Transformation, n equal 2, you mean?
Just two lines.
First.
I mean, if H ++5 is equal to 0, then it's still closed.
I don't know. The point is that only under such transformations, D++ is closed, is invariant. Harmonic derivative is invariant just under this transformation, not under standard.
You mean harmonic derivatives involve
D++,
plus,
yes.
H ++5, right?
D++, yes, D++5. Basic object.
Well, okay, so it's technical problem.
No, technical, but nevertheless, it it is invariant under such transformation.
If it's just 0, H ++5 is 0 right from the beginning. What changed?
No, it H ++m not 0. Why it is 0? I went to.
Well, okay.
I went to linearized level, D++ flat, but all these objects are present in this area. They just passing to linearized level means linearized gauge transformation. That's all.
Okay, Zhenya, I will ask you later.
Yeah.
Sorry.
So using this transformation, yeah. So from the superfields, you can construct some object S1 + 4 S2, which is given just by this transformation by this object. They n equal to supersymmetric by construction, but it turns out that under the gauge transformations, they have the following transformations, and the gauge invariant only in the sum. The sum is gauge invariant. Actually, this linearized level was previously found by Zupnik from some other reasons by reduction of full action of n equal to Einstein supergravity, which was given in a paper by Galperin and others. What component Lagrangians? Like in Yang-Mills, you need to define negatively charged Wilbians. They are given here for some particular case. And then, for instance, Yang-Mills Lagrangian comes from after integration over theta harmonic from this part of the superfield Lagrangian. This you have just standard after integrating over theta harmonic, you have standard FMN square term and some auxiliary fields for this auxiliary tensorial fields, which are 0 on shell. They relate to original T by this shift. And spin 2 also can be find Lagrangian in the same way. It is given by the following expression. It is mainly invariant under the linearized form of gauge transformations, which is just standard free spin 2 gauge transformations, actually. For spin 3 model, despite the fact that we have no nice geometric description for this case, as compared to n equal 2 case. N equal 2 case, we have supergravity, well-defined geometric theory, and go to spin 2 free model by linearization of the corresponding action. Here we have no such hints as in the case spin 2, but it turns out that you can define you can define all the basic objects, namely analytic, in the same way as spin 2. It's just this object are the following one: some triad of gauge fields. These gauge fields with this set of indexes, some vector gauge fields, analog of H ++ 5, and corresponding conjugated spinorial analytic superfields. With the following transformation law, gauge transformation law, which directly generalize gauge transformation law for spin 2 superfields, analytic superfields given earlier. Again, you can go to West-Gemini gauge in this set of fields, and you find the following reducible field content. Actually, spin 3 gauge field, spin 2 gauge field, and the spin 5/2 gauge field, which is described by this fermionic superfields psi. And actually, of shell, you have just 104 plus 104 of shell degrees of freedom, bosonic and fermionic. And on shell, after eliminating of auxiliary fields, we are left with this on shell multiplet with this content. Analog of spin 1 is just spin 2. Analog of spin 2 is just spin 3, and 5/2 analog of spin 3/2. Residual gauge freedom is given by these transformations. Okay, I will take a few minutes from discussion due to the long question of. You have the following residual gauge freedom. It is just analog of diffeomorphisms. This analog of spin 1 gauge transformation, just now spin 2 gauge transformations. And also you have a local 5/2 fermionic gauge symmetry and local Lorentz rotation, but also some additional analogs of Lorentz rotations containing the following set of indices given here. Using this freedom, you can go to the gauge where phi contain only pure spin 3 gauge part and some trace just vector, and this time some vector field. For C, of course, you have irreducible content corresponding to spin 2 field in the environment under this gauge transformations. The spin 3 gauge transformations, the spin 2 gauge transformations. Invariant Lagrangians again construct by analogy with spin 2 and introduce negatively charged Wilbeins, define new n equal to supersymmetric singlet superfields by these formulas, which satisfy the spin flat harmonic flatness conditions, and the following transformations they have these new objects. And it is surprisingly that action is just a full analog of previous action for spin 2 is given by the following expression. It can be checked that it is invariant under this spin 3 supersymmetric gauge transformations. And spin 3 component action can be, after some work, of course, can be found in the standard form. It is just standard form for spin 3 gauge Lagrangian in the spinorial notation. It is invariant under all transformations which were written previously. And of course, generalization to the general integer spin S goes more or less directly. You have to introduce this set of negatively charged, additional negatively charged superfields, but basic ones are analytic, having these charges, harmonic charges plus. And corresponding gauge group also easily found, and can be shown that in the West-Gemini gauge you have just the following spin content, which is given here. Next step, we define analogously this new superfields, non-analytic, and construct the action construct the action completely the same way, and it is invariant under this gauge transformation, like in the case of spin 2 and spin 3. Summary. So we presented off-shell n equal to supersymmetric extension for the theory for integer free spins. For any spin, the superfield content is known. It is just was given. It's just this set of analytic superfields. And for all these cases, we found n equal to supersymmetric gauge invariant actions, which have the same form for universal form for any S. And so it harmonic superspace proved to be a very efficient tool in the case of n equal to supersymmetric high spins as well. And this opens many new directions of research, which are given. Some of them are given here. It is just the construction of analogous formulation for half integer high spins, extension to IDS super background, n equal to superconformal spins, also interesting to construct in this way. And of course, main question is how to introduce interactions. It is just under study, these questions. And also interesting to couple these high spins to hypermultiplets method and maybe to some new analog of hypermultiplets with some additional indices, Lorentz indices, and constructing high spin analog of n equal 4 supernomial means, at least at the abelian limit, because n equal 4 also hybrid of n equal 2 supernomials plus hypermultiplets. If you would know this hypermultiplet analog, then we could construct some n equal 4 high spin fields. And many problems, of course, remains. And so I will finish by this. And thank you for your patience. And of course, warmest congrats. Our magnificent magnificent 7.
Which questions do you have, please?
You told about interaction,
yeah.
But for higher spin, interaction includes higher derivative. You told that you just will replace the...
No, it is first, I mean, I don't know how action would be constructed. I mean that first step is just replace all flat d plus plus, d minus minus by d plus plus, d minus covariantized with respect to standard supergravity with high spin 2.
But it doesn't work for higher spin, even for...
yeah, but it would be high spin would be considered some external superfields with respect to this supergravity, some background superfields. It's the first step, but of course we need to construct the supergravity which will involve all these gauge superfields. I think there is some ideas how to construct this, but I couldn't dwell on this point.
Sorry, and last questions from Zoom, please.
Evgeny, it's Sergey. Hi, I have, thank you for good talk. I have two historical literature comments. Well, first a comment, n equals 2 of shell multiplets were constructed well, in n equals 1 superspace. In my paper with Gates and Sibirikov, I mean, they were realized in terms of n equals 1 superfields, but multiplets were off shell. And well, so in 1999, there was a paper by Segal and Sibirikov, my former students, and they just recast the equations of motion for those multiplets in n equals 2 superspace. So it's not, well, it's not the actions, but the equations of motion they wrote in terms of n equals 2 superfield. So, well, when you say that there are no off-shell multiplets, that's not quite true because we didn't have a realization in terms of n equals to superfield, but multiplets were there. And
Okay,
second comment.
Okay,
Yes.
but the main point is that in this formulation, this off-shell multiplets are given by fully unconstrained analytic superfields. But in all those constructions you mentioned, people use some constrained superfield, n=1 constraint or some standard n=2 constrained superfields, etc. Main point here that this formulation fully unconstrained in terms of analytic superfield. It is main.
That's fine, but the multiplets, well, our multiplets were off-shell. And the second comment, I mean, well, at the end of your talk, you mentioned n=2 superconformal multiplets, and those were constructed in my recent paper with Emmanuel Raptaki.
No, I know this, but the main point is that we would like to construct this n=2 multiplets as extension of a conformal n=2 supergravity in harmonic superspace. Of course, I think that final results should be matched with your result.
Excuse me, let us stop discussion. Thank you, Sergey.
Thank you very much.
The speaker again. Next speaker, second speaker is Gleb Arutyunov, Hamburg. Please put the presentation in Zoom.
Good morning. Hello. You have to give me permission to share my screen, I guess. Mm-hmm.
The title of talk is present on the screen. 25 minutes on the talk and 5 minutes on the discussion, please.
Okay. Good morning. It's my distinct pleasure to talk at Advances in Quantum Field Theory. And I'm very happy to give my tribute to the 70th anniversary of our renowned scientists who paved a number of illustrious ways to the modern understanding of quantum field theory. So I will be talking today about finite dimensional integrable systems of Ruijsenaars-Schneider type, which generalize the well-known Calogero-Moser-Sutherland models. And the interest of these systems is twofold. First, they do appear in various branches of mathematical physics, including quantum field theory. And second, they serve as a testing ground for new ideas and methods in the theory of integrable models. And although I will be concentrating on a particular aspect, namely quantum trace formulas for integrals of hyperbolic Ruijsenaars-Schneider model, as will be clear from my talk, the goal is to put these models in the universal and elegant framework based on the notion of the quantum R matrix. So I prefer to start from something simple and very well known, namely classical integrability, which is encoded into the Lax evolution equation. The commutator form of this equation implies that traces of powers of Lax metrics are integrals of motion, which means in turn that eigenvalues of Lax metrics defined up to the action of the Weyl group are also integrals. So the question of picking up a basis in the space of integrals reduces to the question of picking up a basis in the space of symmetric functions of eigenvalues. And you can choose various bases. For instance, you can deal with the power sums given by integrals ik, or you can resort to elementary symmetric functions, which are coefficients of the characteristic polynomial of the Lax matrix. So in the quantum theory, the situation is similar. Quantum integrals form a ring. And although the analog of elementary symmetric functions for the hyperbolic Ruijsenaars-Schneider model is known and is given by the so-called McDonald operators, the analog of the power sum basis was not known. And this is one of the goals of my talk today, is to present an explicit formula for this basis. So therefore, the outline will be, I will first formulate the result. I will show you these quantum trace formulas. Then I will proceed with derivation, which essentially will be based on the Poisson reduction of classical phase space known as a Heisenberg double. Then I will quantize the reduced space, obtain the quantum model, and finally present a relation of these quantum trace formulas to the McDonald operators. And if time permits, I will briefly touch upon an issue of introduction of spectral parameter into the arising quantum matrix structures. So this work is done in collaboration with my ingenious former PhD students, Rob Klabers and Enrico Olivucci. So first, the result. The result, in order to formulate it, I need a very brief reminder on the hyperbolic Ruijsenaars-Schneider models. So this is a model of n particles moving in one dimension and with coordinates qi, little. And this theory is advantageous to use exponentiated coordinates, qi capital. The Hamiltonian is maybe given by a sum of two terms involving exponentials of the canonical momenta, and these functions which explicitly constructed out of the coordinates, and these functions do involve the coupling constant of the model. This gamma is a coupling constant. Doing a canonical transformation, which essentially amounts to shift of the momentum variables by this quantity here, and making a weak rotation of the coupling constant, this Hamiltonian turns in this form with a characteristic square root, and this coincides with the form originally considered by Ruijsenaars and Schneider. Now, it turns out that these two parts of the Hamiltonian are separately commuting operators. Okay, they do commute between themselves. So in quantum theory, passing to the quantum theory, it's easier to deal with just a half of the Hamiltonian, and then quantization amounts to replacing this exponential of momentum with a finite difference operator. I call it Tj. This operator acts on the space of smooth functions by just multiplying the corresponding coordinate with the quantum node Q. Now, this Hamiltonian exhibits a commutative family of integrals given by a set of McDonald operators. I will show you them later. Now, the result is a family of quantum integrals, actually two families of quantum integrals, ik. K runs from 1 to n. Plus minus two families are reflected in the appearance of plus minus. And this is the explicit formula. And as you see, it's not given by just a single trace, like in the classical case, but a double trace over two matrix spaces. So this formula involves the quantum L operator of the model put in the first matrix space. It also involves the so-called split Casimir element, which is given in terms of standard matrix unities in this way. This Casimir comes transposed in the second matrix space. And you also see that in between quantum L operator, there is a pad, well, in Russian means prokladka, made out of quantum R matrices, which I will discuss later. Now, due to certain commutation relations between the matrix elements of the quantum L operator, one can, using this matrix commutation relation between these matrix elements, one can show that these integrals, they do commute between themselves. So they are forming commutative family. Moreover, in the classical limit, these quantum R matrices tend to 1, and then the whole formula for these two families collapses to the classical integrals. Now let me briefly discuss how you can come to these results. It has been known since the work of Kazhdan, Kost, and Sternberg that Calogero-Moser models can be obtained by means of a reduction procedure starting from a proper phase space. The same is actually true also for Ruijsenaars-Schneider models. In our case, the phase space to start is the so-called Heisenberg double, introduced by Semyonov-Tenshansky. The Heisenberg double is a symplectic manifold which generalizes the notion of cotangent bundle. In order to formulate the corresponding Poisson structure, we need to consider the algebra of functions on the group G cross G, where G is GLN C. So I will pick up two matrices A and B belonging to this group, and the Poisson brackets between their entries defining the structure, Poisson structure of the double, are given by these explicit formulas, which are written with the help of two R matrices, R plus and R minus, satisfying the classical Yang-Baxter equations. From the point of view of a moduli space of flat connections, these matrices A and B can be regarded as monodromies of flat connections on a punctured torus. Now, this double admits an action of a Poisson-Lie group in this way. So Poisson-Lie group G acts, which is GLNC in our case, acts on the elements of the double by a joint action. This is a Poisson-Lie group in a sense that this kind of map is a Poisson map, so it preserves the structure of the double, provided the elements H satisfy this Kleinian bracket with their matrices R plus minus. This map is Poisson, as I said, and moreover, it is generated by a moment map given in terms of matrices A and B by this formula here. So in order to obtain the Ruijsenaars-Schneider model on the reduced phase space and perform the corresponding reduction procedure, we need to fix this moment map to a certain value and then factor out the corresponding locus of solutions over the action of the corresponding stability group of this moment map. Now, the relationship between Ruijsenaars-Schneider models and Calogero-Moser models suggest that the moment map should be fixed to the following value: exponential of gamma, Kaupling constant, multiplied by a special element of the Lie algebra, element of rank 1, which can be conveniently constructed with the help of the n-dimensional vector E, with all components equal to 1. Working out this exponent explicitly, we are led then to solve this moment map equation for the matrices A and B. And in order to do this, it is quite advantageous to use a special parametrization for matrices A and B in terms of two diagonal matrices, Q and P, and matrices T and U, which satisfy a special condition, namely Frobenius condition. Matrices T and U leave this vector E invariant. This decomposition of A and B, or presentation of A and B in terms of these matrices, is unique, and it's dense for elements in GLNC. Matrices T and U satisfying this Frobenius condition, they form a group Well, it's easy to see from these conditions that such matrices form a group, and I will call this group Frobenius group. Further on, introducing an element W, which is just T minus 1 on U belonging to the Frobenius group, the moment map equation can be written in this form. And analyzing also the right-hand side of this moment map equation, you can see that stability group of this element is given by those elements of the Frobenius group, which also leave a vector E by multiplying it from the right. The dimension of the stability group then is n minus 1 squared, while the number of equations to solve here is equal to n squared minus 1 due to the fact that determinant of the moment map is equal to 1 by construction. Also, please note that the matrix P completely decouples from this equation. So now we can solve this equation provided W is required to satisfy this condition, Frobenius condition. Then this equation can be uniquely solved, and this is the answer for this matrix W for its matrix elements. Dimension of the reduced phase space is easily computed. It appears to be equal to n, and it can be parameterized. The reduced space can be parameterized by elements of these two diagonal matrices P and Q. Further, we can introduce on this reduced phase space a matrix L as a product of this W depending on Q with P minus 1 from the right. And working out explicitly, this L has this form, and this appears to be the Lax operator, the Lax matrix, sorry, of the hyperbolic Ruijsenaars-Schneider model. Now, what I need to do further is to compute the Poisson brackets between the components of L and the sort of exhibit integrability through this Poisson structure. And this can be done by raising an expression for L from the reduced phase into the Heisenberg double. This is done by means of this formula here. So L is taken to be T minus 1 BT, where T is the same element which participates in factorization of A. If we plug in the expression for B, then we see that we are back to this expression L is W multiplied by P minus 1. And on the reduced phase space, we are back to this expression here. So it's an extension of L from the reduced phase space into the double. We also see that the dimension of the number of constraints which we impose in our theory does not coincide with the dimension of a stabilizer, which means that in our system we have second-class constraints. So in order to compute the Poisson structure on the reduced phase space, we have to resort to the Dirac bracket construction. And this is a result. The Dirac bracket computed between the components of the Lax matrix on the reduced phase space comes nicely in the quadratic R matrix form. It involves essentially two R matrices, R and R bar. R and R bar explicitly given by these formulas in terms of matrix unities. And we also see that these matrices appear to be dynamical, so they depend on the coordinates of the phase space. This formula also involves the matrix R with a bar underneath. This matrix appears to be a linear combination of R and R bar, this one here, and explicitly given by this formula. Now, if we parameterize P capital and Q capital in terms of P little and Q little, in terms of these exponentiated coordinates, then the brackets between these little variables appear to be standard canonical Poisson brackets. Further on, the compatibility of this Poisson structure, it means Jacobi identity, requires that the matrix R satisfies the usual classical Yang-Baxter equation, and it does so. So it satisfies this equation regardless of the value of these parameters Q. So in this way, we have found an n-parametric solution of the standard classical Yang-Baxter equation. On the top, there are two more equations which guarantee compatibility of this structure. Equations involving R and R bar, and they are truly dynamical because they also involve Poisson brackets of R matrices with momentum variables. Well, finally, let me mention that the matrix R with bar underneath satisfies this matrix appears to satisfy the so-called dynamical Gervais-Neveu-Felder equation. Now, their integrability, namely the commutativity of the family of classical integrals, persists here at the level of the Poisson bracket between the components of the L operator, in a sense that such a form of the bracket, such a matrix form of the bracket, automatically implies that traces of power of L are in involution with respect to this Poisson structure. Now, that was all about classical theory. Now you would like to quantize. And then it seems natural to start from the quantum Heisenberg double, which is associative algebra generated by entries of matrices A and B, modulo these quadratic relations here, involving two quantum R matrices, R plus and R minus. However, I actually don't know how to proceed from this algebra because it's not very much clear how to resolve the second class constraints at the algebraic level. So one needs somehow to find another way to proceed. And indeed, it's possible to proceed without dealing with the quantum version of the double, just by finding proper generalizations of the classical equations involving R matrices, and then trying to solve them and find appropriate solutions of these equations for quantum R matrices. So classical Yang-Baxter equation is obviously generalized to become a quantum Yang-Baxter equation. And these two dynamical equations involving Poisson brackets of R matrices with momenta variables can be now replaced by these relations here, where canonical momentum is replaced now by the finite difference operator, and the effect of the classical Poisson brackets is replaced now by sandwiching the corresponding R matrices between these finite difference operators. Assuming that the theory now is based on these equations, we would like to solve them. And the first observation is that the classical R matrix satisfies this remarkable property that its square is equal to minus R. Then according to the Drinfeld theorem, we can just take as a quantum R matrix the exponential of the classical one, and this is an explicit result. So this is a solution of n-parametric solution of the quantum Yang-Baxter equation. On the top, there is another solution, which I call R minus, and it's related to R plus.
5 minutes left.
Dynamical counterpart. Yeah. Okay. Then we find also the relation for R bar. The relations for R bar, and the explicit solution of this equation is given by this formula. Good. So this is quantization of the classical R matrices. And now we can also quantize the Poisson bracket for the Lax matrices. It results into this quantum L operator algebra. It's a quadratic algebra generated by entries of the quantum L operator. And what is remarkable that this algebra is indeed represented by the quantum L operator of the model, which can be taken to be essentially the same as the classical L operator, except that now exponential of momentum is replaced by this finite difference operator. So this is the algebra, and this is its realization. And all what I need now to invent is an analog of the trace formula for the algebra generated by these relations. So, and this is the answer, which I have already showed. And this answer actually generalizes the formula which has been previously found for the rational case. But now this pad between L operators is given in terms of new quantum R matrices of the hyperbolic model, and it appears rather involved. If you compute explicitly what is in between of these L operators, you see that these are these combinations, these are these products made out of matrix unities and coordinates. Nevertheless, it's possible to show that these are integrals which form a commuting family. Finally, about the relation to McDonald operators. So McDonald operators are finite difference operators, which depend on two parameters, coupling constant parameter omega and the quantum node AQ. They are explicitly given by these expressions here, and they can be obtained from a generating function from a ordered analog of the characteristic equation, coefficients of the characteristic equation, where ordering means that you have to compute this determinant by considering P and Q variables as commuting, and then at the end of the computation, you put all P dependents to the right. And now let me present you a relation. It's quite remarkable between these McDonald operators and the quantum trace formulas. These are where it is. It sort of disappears. Here it is. So the relation between McDonald operators and quantum trace formulas is given by the determinant formulae, which look precisely the same as a classical relation between elementary symmetric functions and power sums, except now in the places where you normally find the usual numbers like k-1, k-2, and so on, 1, and k factorial, you put q numbers constructed with the help of the quantum node in this way. So I think this completely justifies a statement that this integral psi k plus minus represent quantization of the classical traces. Good. Baxterization, maybe I will just put one transparency. One can introduce into this formulas a spectral parameter. In principle, it's not needed for the hyperbolic model. Integrability can be exhibited without it, as I have just done. But in some problems, it's useful to have a spectral parameter, for instance, for separation of variables or for generalizations to the elliptic case. So in this case, the quantum operator depending on the spectral parameter is a linear combination of an original quantum operator and the gauge transformed quantum operator. This way you have lambda spectral parameter and deformation parameter and slight presence of quantum node here. That's because of the ordering problems of L and Q. It must be there. Now this spectral dependent L operator satisfies this quadratic algebra now with with matrices which do depend on the spectral parameters. Explicitly, they are given by these formulas, and they involve finite dimensional R matrices R plus, R minus, and R bar, which I have already discussed, and also a new element X. What is interesting is that the compatibility of this quadratic algebra requires that now this quantum spectral dependent R matrix does not satisfy the standard Yang-Baxter equation, but rather it's a modification where some of the spectral parameters are scaled with the help of the quantum node Q. And the same is also true for equations involving R and R bar. So these equations for quantum R matrices satisfied by these explicit formulas, they provide compatibility of this quadratic algebra. Good. Finally, you can prove that these algebraic relations imply that traces of L operator evaluated for different values of spectral parameter do commute between themselves. You can also define a notion of a quantum spectral curve by taking an ordered version of the characteristic equation. Then it appears that coefficients, lambda-dependent coefficients, which you get for this characteristic equation, are of this type. So lambda dependence completely factorized, and you are back to McDonald operators. Good. This is basically all what I wanted to tell you about these nicer matrix structures in the theory of hyperbolic Ruijsenaars-Schneider model. Well, it's clear from the discussion that the key tool in this matrix construction is a Poisson reduction of the Heisenberg double. And from this point of view, it would be quite interesting to get the quantum operator algebra directly from the quantum double. and further extend these structures to other models, including those with internal degrees of freedom. And recently, there has been a lot of progress in this direction. So with this, I would like to finish and send with admiration all my best wishes to our jubilars. Thank you.
Thanks, the speaker. A nice talk. What questions do you have?
Okay. Is it possible to extend all these things to compactified Ruijsenaars-Schneider models?
You mean compactification of momentum?
Yes.
I think so, but I have not done this explicitly. And yeah, it would be interesting to see if there are certain non-trivial modifications which you have to do for this case. I don't see an immediate obstacle why it cannot be done, but I guess accurate construction is needed. What I'm doing here, what I'm doing here is an algebraic quantization. So I don't care actually about reality conditions. So for me here, all variables Q's and P's are complex. So the only question is if imposition of proper reality conditions is compatible with these structures here. This quantization is purely algebraic. It's a framework of algebraic or holomorphic, better to say, integrability.
Here's a question from Zoom. Alexei Isaev.
Gleb, when people say about Ruijsenaars-Schneider model, they sometimes mention double-affine Hecke algebra, unique algebra. Are there any relations of your algebraic structures with double-affine Hecke algebra?
It's a good question. I know, of course, about these relations. It goes more in the direction of Dunkel polynomials and Dunkel operators. This is not what it plays an important role in my construction here. I admit that there should be a relation, but it requires to be seen. I don't know how this must be implemented or how this goes to be implemented in this approach.
Okay, thank you.
Questions? Yes.
For wish list, you showed in the quantum case that the model deformation parameter, which in the limit of 0 gives the classical case, if you expand, you might obtain hierarchy of integrable systems at 0 or the classical and higher order. The second is that when you have several integrals, you can construct not classical Poisson structure, but higher number Poisson structures. And higher structures has the Poisson part, the coefficient functions, simpler and simpler. So reducing from the higher structure to the lower one at the bottom, the Poisson structure, you obtain hierarchy of these Poisson structures, and they are also interesting. Thank you.
Mm-hmm. Yes, I think I totally agree with you. Yes, I agree with you. Yeah.
Let us stop the discussion. Thanks the speaker again. Next speaker is last speaker in this session, Gregory Korchemsky from Saclay. Please share the presentation. Please.
Do you hear me?
Oh, okay.
Yes, please. Very good. Thank you very much. So let me start with joining all of you and congratulating our esteemed colleagues and friends on the 70th anniversary, and I wish them many happy returns. So let me also mention that among 7 gentlemen which you see in this picture, there is one which has a very special role for me. As you will see in a moment, I had a very special relationship with him. And let me start specifying the title of my talk. So the title of my talk at the beginning of the program was kind of very ambitious, and I will explain you why it was very ambitious. And secondly, you might ask yourself for the reason why I put 35 years, and you will see in a moment what does it mean. But to be more concrete, I will be talking about a very special aspect of high energy QCD. Basically, I will try to put forward very speculative questions, namely how far is QCD? By QCD, we mean theory of strong interaction, four-dimensional theory of strong interaction, from maximally supersymmetric Young-Mills theory. And you have heard from the first talk this morning, this is a very special theory. It has maximal supersymmetry, is EV finite, and at first appearance, there is nothing in common between the two. But hopefully, you will see by that of my talk that actually the answer to the question is not that obvious. So let me first explain you what happened 35 years ago. And actually, what happened 35 years ago is that I just arrived to Dubna as a French PhD student, and I had the privilege to work in a very active QCD group, which was led by Anatoly Vasilyevich Efremov, Anatoly Radyushkin. And basically, the reason why I put the title of my talk so ambitious, because being young, you're always ambitious. And more or less, this was the time when everyone was very excited by QCD, specifically P2PD QCD. And this was the reason why I launched into the program, which was very ambitious. And the punchline of the project was to understand the infrared divergences of scattering amplitude in P2PD QCD. And if you wish, my talk today is somehow could be sort of a continuation of the project which I started 35 years ago with Anatoly Radyushkin. So let me give you some background of how things look like that 35 years back to Dubna. Let me remind you that it was a time there was no personal computers, no internet, no archive. So basically the only source of the information was library, and Dubna library was great. And there was some limited access to preprints, which were arriving to Dubna quite regularly. Not to mention that there was no free access to Xerox copies, all the kind of complications. But let me also mention there was a very special source of the information in my case, which was desks in Anatoly Radyushkin's office. So this is not actual picture, but it reflects quite good sense the way how it looked like. So even though you might think this is a complete mess, but if you look carefully under some search, you would find some interesting papers appearing on this desk. And actually, few of those papers I will mention later. So let's come back to research project, which I mentioned at the beginning. So the project was aimed to understanding scattering amplitudes in high energy QCD and in general in gauge series. And it was quite kind of known by that time that if you start thinking about scattering amplitude, so for example, here on the left-hand side, I have shown you to scattering, this gray blob stands for the S matrix. So if you stay within P2PD approach, we're just drawing Feynman diagrams. You have to integrate to the moment of particle exchange. And it was kind of known that if you go to high energy limit, by which I mean omega this time with variance being large, this diagram simplifies. Namely, it turned out that if you're looking for the asymptotic behavior of this amplitude, you will see the dominant contribution come from very special part of the integration of phase space, which go under the name hard, jet, and soft. So by hard, I mean process when all particles exchange have momentum or the external kinematical invariance. This block with J stands for the jet functions, which describes the possibility for incoming particles to split into collection of particles with a light momentum before the end of the collision. And finally, there is this red blob, soft function, which takes into account the possibility for those particles to exchange by soft gluons before they actually enter into the collision. So this diagram reflects the way how we understand amplitudes these days, namely those amplitudes could be factorized in a certain way into the product of hard, jet, and soft function. And if we're about to understand infrared divergences of amplitudes, this is a soft function which interests us most. So once again, this soft function describes the possibility for the particles to exchange soft gluons before they collide. And if you're thinking about the line physics, this is actually classical physics, namely these particles which enter the collision, they look like the source of the color charge. And what soft function carries about, it carries about momentum in which particles propagate and their color charge. And the consequence, interaction of those particles with soft gluons amounts to opinion of acanal phase. And in the case of non-abelian gauge fields, acanal phase is given by the integral of the gauge field along the classical trajectory of the particles. So the particles goes along classical trajectories defined by their momentum, and this integral basically is the integral of classical trajectory, which in this case becomes semi-infinite ray along momentum pi from infinity to the zero where collision takes place. And therefore, if you take this picture and you go to the original process, when, for example, here you have 4 particles scattering each other, each particle gives rise to the scattering phase, and in total we have the object which is product of 4 matrices, each matrix defined by the Wilson line, each Wilson line oriented in the direction defined by the on-shell momenta of the particles, either incoming or outgoing, which explains the minus here. So now, if you want to understand structure of Fred divergences, we have to find the way to compute these objects exactly. And this turned out to be quite a trivial task, basically because as matrix in non-Abelian gauge C is quite a complicated one, so you have an interaction between gluons, and maximally good hope to understand P2 expansion of this function to 1, 2, 3, etc. loops. So how to compute this function? And at that moment, I refer to what happened previously, namely just search carefully on Anatoly desk and you find a couple of papers, which looks to be remotely related to what I was discussed before. Namely, those days, which is 80s last century, people were discussing the possibility to formulate Young-Mills dynamics in terms of collective variables, which in this case turned out to be Wilson loops. So the Wilson loops defined as follows. So you have particular gauge C, let it be QCD. So you take particular closed contour in Minkowski spacetimes and you integrate of the gauge field along contour, taking care of the ordering of the color indices for TA being generator of the SUN gauge group. And here I put the index R just to specify you have a freedom in choosing the representation of the gauge group to be whatever you like, either fundamental for quarks or adjoint for the gluon. So this R specifies representation and this index R will play an important role as follows. So this object is perfectly gauge invariant function in Young-Mills theory. And we ask the question, what kind of equation you could formulate for this object, at least in classical theory? And those are celebrated Minkowski and Migdal equations, which are equation equivalent to the equation of motion in classical theory. And the next step was to quantize those equations, namely try to understand whether they're consistent with the underlying quantum dynamics. And actually, one of the papers which I mentioned was paper by Lekov back to 80, who actually noticed that if you start quantizing these objects, maybe start taking account quantum corrections to the Wilson loop, you will find there is a problem. The problem appears when the integration path has a cusp. For example, here you have smooth path everywhere except the single point, where there is cusp angle phi. And if you're computing the simple diagram with one gluon exchange between around this cusp, you will find integral like that. And you could easily convince yourself this integral develops ultraviolet divergence when both points approaching the cusp point. And this divergence comes as a very special function of the angle, which is this one. I remind you, phi is the cusp angle, with the coupling constant, and here you have quadratic Casimir. So the fact that this contribution is proportional to quadratic Casimir as a representation which is defined by the representation of generators goes under the name of the Casimir scaling. So here you have Casimir scaling with the one loop corrections depending on cusp angle. And let me emphasize, these are ultraviolet divergence. And then you ask the question, what's the issue which we discussed before, namely infrared divergence of scattering amplitude, have to do with this very bizarre UV property of the Wilson loops? And to answer this question, let's consider a very special process, simplest one, when you have scattering of heavy particles of some external potential. So you have heavy particle, which mass mq, which moves certain velocity v1, then it goes some scattering of external potential, changes its direction to the V2 and goes to the final state. So once again, you're dealing with infrared singularities. You go to the Wilson line picture. Here you have one Wilson line which goes from minus infinity along velocity V1, velocity V2, and you want to understand how infrared divergences looks like. So in momentum space, you will get integral which look like that. So k square comes from the gluon propagator, and these two other propagator correspond to this Wilson line. And you could easily see from this integral that it indeed develops infrared divergences when k goes to 0. Integral obviously is logarithmically divergent for small k. At the same time, you could also see that the integral is also divergent in the UV because it's homogeneous function of k. So therefore, if you were very careful with introducing regularization, you will find that the integral will be both UV and infrared divergence. And since there is no any other scaling game, it ought to be proportional to the logarithm of the ratio of those two scales. And since UV scale appears in the numerator, you already knew from the previous paper by Polyakov that coefficient in front would be this special anomalous dimension, which is called cusp anomalous dimension. So this simple exercise tells you that what's special about this Wilson line, which we encountered in the study of infrared singularities, that they carry both infrared divergences from the way how we constructed them, also some artificial UV divergences, which are intrinsic property of the Wilson line with the cusp. So in this way, you established one-to-one correspondence between infrared singularities of scattering amplitude and UV divergence of the cusp Wilson loop, which led you immediately to the normalization group equation, which is quite a trivial one because it tells you that scattering amplitude, the function of infrared cutoff, satisfies the same evolution equation as UV Wilson loops with the same anomalous dimension. The only difference, the coupling constant in stereo like QCD will be normalized not on the UV scale, but in the infrared scale. But the function is exactly the same. So now if you go to more complicated objects, when, for example, you have scattering of many particles, then you have to deal with situation when all these exchanges carry color. And in general, the corresponding object will be not simple function of the angle, but will be matrix. But simplification occurs if you go to the planar limit. So in the planar limit, you restrict yourself only to the diagram that you would draw on the plane, like this one. And then in this case, you could show that the corresponding matrix becomes diagonal, and it reduces to the sum of the cusp anomalous dimension, and the sum goes over all possible wedges, which are formed in this case by 4 lines, and the corresponding angle will be exactly the angle between neighboring lines on this picture. So in this way, cusp anomalous dimension, which appears kind of artificial property of the Wilson loops, turned out to be a very physical object if you go to infrared singularities. So in this way, computing cusp anomalous dimension from Wilson loop side, you will be able to predict structure infrared singularities in QCD and in any other gauge theory. So that is the reason why cusp anomalous dimension becomes kind of a very important physical observable in QCD in any gauge theory, and it has very interesting properties if you go to different limits. So the first limit corresponds to the limit when this cusp angle becomes small. This is exactly the limit which you encounter in heavy quark physics. If you're thinking about this line corresponding to the heavy quark, then it gets deflected by a certain angle, and this angle could be small. And in this case, when you span a small angle, you will find the coefficient. The first time with expansion will be phi squared. The corresponding coefficient actually is known from quantum electrodynamics to be so-called Bremsstrahlung function. In quantum electrodynamics is one loop exact, but in QCD, as any other abelian gauge theory, is quite a complicated function of the coupling constant. The second interesting limit is the one when you have backtracking Wilson loop. Namely, you have these 2 segments of the Wilson loop, and you have an angle between them which is almost goes to 0, or in terms of our angle phi goes to pi. Then if you look for the expression which you've seen on my previous slides, you will see that already at one loop, cusp anomalous dimension develops a pole. And actually this pole keeps going to higher number of loops, and what happens is the coefficient, the residue of that pole, turned out to be related to so-called static quark and quark potential. Up to some corrections which have to do with conformal symmetry breaking. Another way, if the theory were conformal, like maximally supersymmetric angular theory, it will be exact statement. But in series like QCD, we have the zero beta functions. This relation holds up to corrections proportional to the beta function. And finally, the last limit is the one which corresponds to the scattering of massless particles. So far we were discussing massive scattering, but if you go to massless case, in this case, you're dealing with angle phi, which is large hyperbolic angle. Another way, you're dealing with cusps, where both segments are very close to the light core. In terms of the angle, it corresponds to a situation where this cusp angle becomes pure imaginary, goes to infinity, and then the cusp anomalous dimension could be shown to have exact asymptotics, which is single logarithmic one in this variable 1 of x. Or if you translate it in terms of the angle, it will be proportional to this large angle with the coefficient, which is known as light-like cusp anomalous dimension. And this light-like cusp anomalous dimension proved to be very important physical observable because it appears in various resummation approaches in high-energy QCD. So in this way, I presented you a framework which was developed 35 years ago, that once you knew cusp anomalous dimension, you would be able to describe different physical limits. And basically, this is why it's so important. But now let's come back to the question which I formulated in the title of my talk. So I promised you that to show some relation between QCD and maximally supersymmetric angular theory. So why don't we consider the same framework, cusp anomalous dimension, Wilson loop, in a more general class of theories? So instead of dealing only with QCD, when you have Dirac fermions coupled to the gauge field, let's go to the supersymmetric extension of the theory. And in more general, let's consider this theory when you have certain number of scalars and fermions, all in joint representation of S gauge group. And once you have this and S and F and F as a free parameter, you could basically recover all supersymmetric field theories by fine-tuning those numbers. For example, for number of fermions, while fermions being 4, a number of real scalars being 6, it will be corresponding exactly to this special theory n equal 4. And why nickel 4 is special? So it's special because, as I already told you, it has quite remarkable properties. So it's UV finite, so it has a conformal symmetry. It possesses dual gauge gravity duality, adhesivity correspondence, and last but not least, in the planar limit, it believes to be integrable. By this, we mean that as finite amount of time, we'll be able to solve this theory in the planar limit exactly. And let's, in the context of Caspar anomalous dimension, this translates into the statement that actually this light like Caspar anomalous dimension, which I introduced you previously, it's known in planar n equal 4 theory for any value of the coupling constant, which is quite a remarkable result. So having said that, I've repeat again the question. So we have Caspar anomalous dimension, which is defined in these two seemingly different series. And the question is, are there any common properties between those functions in these two series? Well, let's try to answer this question by just doing some concrete calculation. So let's open up perturbative calculation toolkit and try to compute this Caspar anomalous dimension in powers of the coupling constant. So I told you that you expected to have Casimir scaling. So this quadratic Casimir, which define a representation in which a gauge field circulated along the contour, give you coefficient in front. And what you have inside the bracket, coefficients in powers of the alpha s, 1 loop, 2 loop, and 3 loop. So 1 loop you already seen. At 2 loop, you're expecting to have different color structures, one of them coming from the gluon diagram, another coming from the Fermi loop. If you go to 3 loop, it becomes more complicated. And here I just gave you some sample diagram. For example, this 3 diagram will give you contribution which enter into this 3 function with the red prefactors, and so on. So what do we know about those functions? So 1 loop corrections, which was found by Polyakov, 80. So the one with Anatoly Radyushkin, it took us 7 years to compute 2 loop corrections, and it took us only almost 3 decades to get it to 3 loop together with Andrei Grozin, Johannes Hen, and Peter Marquardt, which give you kind of impression, difficulty of the calculation. And finally, I put here 4 loops. So yeah, you might ask yourself the question, why should I go to 3 loop? I go to 4 loops. So I will show you later that there is good reason, because something happened at 4 loop. But still, you could see from this time span that it's quite complicated calculation. So now let me present the result. So let's start from 2 loop. So at 2 loop, you have, once again, Casimir scaling, 1 loop function. At 2 loop, you have contribution of the gluons, contribution of the quark. And here I put in the red some function A1, A2, and 3. So this is a special function. And those function depends on the angle. So angle appears through various variables, x, psi, y, doesn't matter. So this function A1, A2, and 3 are given by linear combination of yet another function, which goes under the name of harmonic polylogarithms. So these functions are defined iteratively. So if function has only one index, it's basically logarithms. It has 2 indices, iterative integral with a measure which is rational function of t. So those functions, HPL, they have also quite remarkable properties. And one of the properties, you could assign them certain weights. So the number of indices which appears here goes under the name of the weight. And if you now look for this function A1, A2, and 3, you would easily convince yourselves that actually index A1 corresponds to the fact the function has weight 1. A2 has the fact that function h here and there has weight 2. And pi square also has weight 2. So in this way, you see that at 1 loop, you have function weight 1. At 2 loop, you have a mixture function weight 2 and 3. And quarks come with weight 1. Very good. So now let's go to 3 loop results. So calculation becomes way more complicated. Once you have now 3 different color structures, correspondingly you have 3 different functions. The one coming from the gluon diagram like that, 2 fermion loops, and 1 fermion loop comes with 2 different color factor. So now let's start looking for those functions. Let's start from the gluon diagram. So this gives you most complicated contribution. So those which here in red, this is a function which are more complicated than the previous one. But once again, they have a feature, they give a linear combination of those HPL functions with the total weights given 5, 4, etc., etc. And this is a new function, new in the sense that they didn't appear to 2 loop. And those functions A3 and 2A1, those which you've seen in my previous slides. So you see that this gluon contribution gets admixture of the function which you've seen previously at 2 loop plus some new function. And now notice that if you go to the contribution with fermion, you will see that those contributions come with a function which previously appeared to 2 loops. There is no new function which appeared 3 loop and higher. These will be very important. So now let's try to see whether this result goes through various checks. So first check, I told you that if you go to the limit of large angle poor imaginary angle, which corresponds to the massless particle scattering, the cusp anomalous dimension should be a linear function of the angle. And indeed, you take this real result, you verify indeed it's linear function of the angle, with corresponding coefficient with this light-like cusp anomalous dimension. And here the expression for this cusp anomalous dimension to 3 loop. So once again, you have Casimir scaling, which is positive with the perfector, and here you have 1 to 3 loop coefficient, which come with quite complicated combination of special numbers, zeta of 3, pi's, etc., etc. And then you could also verify that calculation done by those people many years ago, indeed, we agree with their results. So now you go to different class of series, those which I defined before as a supersymmetric extension of QCD. And for example, if you go to the series which is n=4 theory, you will find much more compact expression. One of the reasons why it's much more compact, because those parameters, number of fermions, number of scalars are fixed, and therefore then you don't have much freedom. But what's remarkable here, you will find the expression has very simple form, with 2 3-loop coefficient being powers of pi, and exactly the same numbers appears previously in QCD calculation at 2 and 4 loop, at 2 and 3 loop. These are not accidental, because we know that n=4 has some special feature, namely it captures the most complicated part of the QCD result, and here you just have another manifestation of the general feature. But still, you have to agree that the expression for QCD and n=4 look quite different. So there is no way you could map one expression to another one. Those are 2 completely different expressions, and at first glance, there is nothing in common between them.
4 minutes left. 4 minutes left. 4.
Very good. So now let's try to play the following game. So we're looking for the expression of cusp anomalous dimension part of the coupling constant. But coupling constant is not physical quantity. We are free to choose any other parameter of the expansion. And now let's choose cusp anomalous dimension, light-like cusp anomalous dimension, as a parameter expansion itself. So this amounts to some finite redefinition of the coupling constant, which means that if you were to expand cusp anomalous dimension the powers of this new coupling constant, you will get some set of the relations which tells that the new coefficient of the expansion relate to the previous one through some linear combination. On the right-hand side of these formulas, those functions gamma and k, they do depend on number of fermions, number of scalars. So each of these functions separately depends on the particle content. So they're different QCD and supersymmetric series. But what will happen if you plug in into this formula? What you will find, something interesting happen. So what you will find is that once you do a QCD calculation, you will find that this function QCD will not depend on number of fermions, which means it's exactly the same as any Young-Mills theory, poor Young-Mills theory with no fermions. And now if you go to those class of supersymmetric series which I defined previously, you do repeat the same calculation, you will find it also don't depend on number of fermions and scalars. And what does it mean? That this function omega, at least to 3 loops, it's universal in any gauge theory. Doesn't matter, will it be QCD or n=4 theory. And here's the expression. So there's a function, universal function in any gauge theory, which has Casimir scaling, with the coefficient from the power of the coupling constant being those HPLs which defined previously. So now, do we expect this to hold to high number of loops? And unfortunately, the answer is no. And this has to do with the following facts. That once you go to 4 loop, some new phenomenon happens. And this phenomenon actually was anticipated a long time ago by the gentleman. And it has to do with the fact that starting from 4 loop, you have to deal with some new Casimir, Casimir color factors. Those factors which break Casimir scaling. So they will not be coming anymore with factor of CR, which complicates things enormously. And as I told you, at present, there is no calculation of the full cusp anomalous dimension to 4 loops. But what you can do, you could do simplify your task by going to the light-like cusp anomalous dimension, the one which appears in large angle limits. So until last year, there was only one piece missing. So contribution from fermions and scalars have been computed by 2 different groups, including another jubilee, Volodya Smirnov. And the only missing part was the one coming from the gluon diagram. So with some efforts, we did compute the contribution. Here it's given, and which becomes a last missing piece for the QCD. And also it gives you some prediction for n=4 theory. So I told you for n=4 theory, we expect integrability to predict planar piece. And here we have a planar piece, which is given by the sum of 2 terms, the power of pi and zeta of 3. And here I show you the first time result for the non-planar contribution. So the non-planar contribution comes with the coefficient 1 of the n square. Why? That's why non-planar. But what's remarkably, the corresponding coefficient looks quite similar to the planar one. So this calls for the explanation. because we know that integrability approach works well for the planar contribution, but we don't know yet whether it works for the planar one. But this somehow suggests that something goes on. Finally, let me finish with a few questions. So I try to convince you that this Caspar anomalous dimension, which was introduced 35 years ago, is still very interesting physical quantity. It still survives through all these perturbations, all going from NCL4, etc., etc. Also, coming back to the question which formulated at the time of my talk, I think I try to convince you that NCL4 is much closer than you might think. You have to put your eyes carefully just to see there is something goes on. Indeed, there is a relation between the two. We observe this relation to three loops, but actually don't know why it should be there at first place. So it's there, but we don't have an explanation. It's really to understand the reason. And last but not least, Caspar anomalous dimension is only one of the quantities which we could consider in both theories. What about other quantities? Are there some other what we call universal quantities which look the same in two theories? And recently there was some progress on this, especially in context of unequal to two supersymmetric Young-Mills series. And finally, all this kind of give you a very strong hint that something goes on in QCD. So we're about to recover some new symmetries which are hidden in QCD once you go from classical to quantum level. And what I described during my talk is yet another hint to this. Thank you very much for your attention.
So the speaker on the spot. What questions?
I understand that your theory is applicable only for quarks and gluons. Do you have any idea how to apply it to white observable particles, pions, nucleons, photons, especially virtual photons, regions? I understand that this is the problem of confinement, but unless you think in this direction, this will be only of academic interest.
Thank you very much for your question. You're perfectly right. And as I told you from the very beginning, I took a perturbative approach side. And I wish I knew how to describe scattering hadron in QCD, but we are not there yet. Definitely, the high, if you compare two series, QCD and NCL4 theory, maximum we could hope for that dynamics at short distance QCD could be captured by NCL4, which from point of view of QCD is trivial theory because it doesn't have any bound states. Once you mentioned the radial limit, let me tell you something about comparing these two series. So if you're thinking about QCD and you go to radial limit, you're expecting to find radial trajectory where you put your hadrons. But there is some part of the radial trajectory which you go to negative values of t, which you could see if you just do calculation perturbative. Another way, you go to radial limit of scattering amplitude, even perturbative QCD, and you, for example, will recover BFK Pomeron. So BFK Pomeron is a perturbative part of what's called real Pomeron trajectory, and which has some physical meaning. And actually, there was a lot of activity was going on to find traces of BFK Pomeron and QCD analogy. So in this case, NCL4 also gives you some insight because one of these universal quantities which I mentioned previously, it has to do with the radial trajectory. And indeed, there was some progress how you could compute radial trajectory in perturbative QCD using NCL4 insight. But you're perfectly right, we're quite far from understanding perturbative confinements in QCD based from NCL4 analogy.
Thank you very much for your interesting talk. One question. You mentioned that in the relation between Caspar anomalous dimension and static potential, there is the term which is proportional to the beta function and violate conformal symmetry. Question. Whether this term is checked at the 1, 2, 3, or 4 loop level? And what is the order where it is explicit, the factorization of the beta function is checked explicitly in this relation?
Andrei, thank you very much for the question. First of all, to check correction to the potential, you have to have Caspar anomalous dimension as a function of the angle, which is available to 3 loop. Now, if you go to the potential, it would, if you go to that relation which I have shown you, it would give access to 2 loop potential. So these 2 loop potential have been computed a long time ago, and right now there is even 3 loop potential. So if you take 2 loop potential QCD expression and you compare with the residue at the pole of the 2 loop Caspar anomalous dimension, you will find the difference, which is exactly 1 loop beta function multiplied by, let's call it 1 loop anomaly. This one loop anomaly we identify. In our paper, you could find explicit expression. Now, to get full power of the 3-loop result for the potential, you have to go to 4-loop Caspar anomalous dimension. And we are not there yet. There is some limited success in computing this 4-loop Caspar anomalous dimension. There were some different Casimir structures have been computed, but we are not there yet to give you full answer for this 4-loop Caspar anomalous dimension. But you could turn logic around to say that having potential to 3-loop, you could give some consistency condition for expected result for the Caspar anomalous dimension to 4-loop.
Okay, excuse me, whether I understood you correctly that to check this, the existence of the beta function at the 2-loop level, it is necessary to get the complete result for the Caspar anomalous dimension at the 4-loop level. Is it true?
No, there is drop in one loop. There is drop in one loop going from Caspar anomalous dimension to the potential. But if you're talking about the anomaly, you're talking about some anomalous term. So this anomalous term is proportional to beta function.
Okay.
So this anomalous term will appear with beta function multiplied by something. So this something, let's call it anomaly. So this anomaly also will have some P2 expansion.
Okay, thank you.
And last questions from Zoom.
So thank you, Grisha, for this very clear and very interesting talk. I noticed that your K of alpha has uniform even weight. So when you go to the next order, do you think you'll see zeta 5,3, or do you think that this quantity is purely zeta valued?
So thank you, David, for the question. The answer goes as follows. So if you're staying within n equal 4, so let's start from something which we know very well. So this n equal 4, I told you what you have here, these are first two terms of the expansion of the function which we know exactly. Now let's do the following. Let's look for the expression of the function at V coupling. So what you will find is that to any given order of P2 V coupling expansion, it will have only zeta function, not multi-valued. However, and these are something also interesting observation which we don't have explanation yet. Now let's go to strong coupling. So I told you this function we know exactly. So now let's go to strong coupling and see what will happen to strong coupling if you're expanding this Caspar anomalous dimension in inverse powers of the coupling constant. So the ICFT give you some information about that. What you will find, you'll find a series in one of the square root of the alpha s, and the coefficient in this expansion will be zeta function of odd arguments plus Dirichlet zeta function of odd even argument. So powers of pi get replaced by yet another zeta function, which is not order one, but Dirichlet one. So these are what I want to say is that at strong coupling, you have V coupling when you have special class of special numbers which enter P2 expansion. You have strong coupling. Some numbers propagate from weak to strong coupling, like zeta of odd arguments. But pi's or zeta values of even arguments are disappearing and get replaced by another one.
But on your next slide, you had zeta 3 squared.
I'm
yes?
sorry. Let us stop the discussion.
I could discuss. We'll discuss later.
Thank you.
Send the speaker again.
So let us start our next session. Our next speaker is Ioseph Buchbinder from Tomsk. His title is on the structure of 1 and 2 loop divergences in 6D supersymmetric Mills theory. 25 plus 5, please.
So I'm grateful to organizers for invitation to give a talk. My congratulations to the jubilars, and I wish them good health and new creative successes. So my talk is devoted to supersymmetric quantum field theory. Okay, the talk is based on the series of papers published in collaboration with Evgeny Ivanov, Boris Mezvikin, Kostya Stepanyan's, and everything is published. The papers can be found in the archive without any problems. First of all, I would like to start with some motivations. Why this activity is interesting? There are at least two motivations. First goes from string theory, second from the quantum field theory. From string theory, I can say that specific features of the string theory is the appearance, existence of so-called d-branes, which are d+1 dimensional surfaces in the Minkowski 11-dimensional space. It was proved that these d-branes are associated with supersymmetric extended field theories. So we can say that study supersymmetric field theory in high dimensions, we try to understand the quantum correction, the quantum structure of superstring theory in the low energy limit. Okay, but from field theory, the extended supersymmetric field theories possesses many symmetries. There are explicit symmetries like a gauge symmetry, global symmetry, supersymmetries, and there are hidden symmetries. From quantum fields point of view, it's interesting to organize the quantization of these models in a way with presentation of all explicit symmetries and preservation of hidden symmetries. So it means there is a problem of formulation, how to formulate quantum field theory with these properties, and second, how to organize the calculations with preservations of all symmetries. As a result, we will study effective action and try to understand the structure of divergences, normalization, and so on. Another point, another interesting point of extended quantum extended supersymmetric field theories is the possibility to construct the new supersymmetric invariants as a corrections to effective action. Sometimes the new invariants is impossible, very important for different aims. For example, in cosmology, the people try to construct the new supersymmetric models, and they need some new invariants. Okay, so let's continue the motivations. First, there is a great number of particles, of papers, sorry, to describe the quantum structure of supersymmetric theories, which can be obtained by dimensional regularization from dimensional reduction from superstrings. This direction was initiated by cybercomputer. Another motivations also related to string theory is a so-called description of M5 brands. Hypothetical M5 theory is characterized by two types of extended objects, M2 brane and M5 brane. So M2 brane is associated with three-dimensional extended supersymmetric field theory, and recently the corresponding field theory was constructed by Bagger, Lambert, and Gustafsson. It has turned out to be three-dimensional n=8 supersymmetric gauge theory with this very interesting gauge structure. Another brane, M5 brane, also is related to six-dimensional gauge theory, but corresponding Lagrange description is still unknown. Another direction of motivations, there was some activity to understand the structure of divergences, extended supersymmetric field theories in high dimensions. First, it was pointed out by Green, Schwartz, and Brink many years ago that if analyze the superstring amplitudes and make reduction to 6 dimensions, it turned out to be that the corresponding Young-Mills theory, 6-dimensional and 1,1 gauge theory, is on shell finite. This analysis was continued by many people. For example, There was analysis based on the on-shell supersymmetries, gauge invariance, and possibility to make the field redefinitions. It was done by Hofstede, Vassart. They also confirm this result and shown that it seems this theory can be finite, on-shell finite. Then there were the direct calculations, one loop and two loop, the divergences in this theory. It was synthesized by paper by Franklin and Seikin, then Marcus and Saniotti. Has also studied the structure of divergences. It's interesting to point out that the paper by Marcus and Saniotti is just the paper where they firstly calculated the two-loop contribution to divergence of Einstein gravity. It turned out to be there should be the same technique to study the two-loop divergence in Einstein gravity, and the six-dimensional Young-Mills theory. And the most detailed calculations were done by Borg, Kazakov, Kompany, Tolkachev, and Zlasenko. They studied the structure of divergences in 6, 8, and 10 dimensions up to the 4 loops. And generally that looks like on-shell divergences in maximally extended 6-dimensional super-Young-Mills theory started 3 loops. On-shell divergences in 8-dimensional and 10-dimensional super-Young-Mills theory starts at 1 loop. And there is a natural equation, what will be off-shell. This is just the aim of my talk. Okay, before to discuss calculations, let me remind the notions. So you know there are many versions of supersymmetry. n=1, n=2, n=10, and so on. Many versions. The simplest n=1 supersymmetry, all other supersymmetry are called the extended. And there are 2 ways to formulate the supersymmetric theories. One is so-called component approach, where the field theory, where the model is formulated in terms of conventional bosonic and fermionic fields. Another way, which works in some cases, is called superfield approach, where we work with superfields, where the function depending both on bosonic coordinates and some number of anti-commuting Grassmann variables. As the coefficients of expansion superfield in anti-commuting coordinates are the conventional bosonic and fermionic fields. Both formulations have their advantages and disadvantages. Advantage of component formulation means that there is a close relation with conventional field theory. This approach is useful when we study solution of classical equations of motion, or when we study scattering amplitudes. But disadvantage is the supersymmetry is not manifest. In superfield formulation, there is a manifest supersymmetry. It's very convenient in quantum field theory to study off-shell effects, like finding the effective action or proof of the normalization theorems. However, there is some puzzle. The superfield approach is useful when we operate with so-called unconstrained superfields. But in many cases, it's not clear how to do that. If superfields satisfy some constraints, they are not the independent functional arguments of action. We cannot differentiate with respect to the superfields. We cannot calculate propagators, vertices, and so on. And the reason of that in extended supersymmetrical theory, we have too many anti-commuting variables. And to make it shorter, we impose some constraints. They are not dynamical constraints, and no derivatives with respect to space-time. But nevertheless, the constraints and not very clear how to work with them. And the best, what we know up to now, the unconstrained formulation is given by harmonic superspace approach, where there is a real way to solve the constraints, but not in the initial space. But to solve that, the people invented new type of superspace. So this is just, I will work with the 6-dimensional N=1,0 gauge theories in harmonic superspace. Okay, so before to calculate, let me make discuss some relation of n equal 1, 1 Soberon-Mills theory and n equal 4-dimensional Soberon-Mills theory. The feature of 6-dimensional superalgebra is two types of independent supercharges. And it means we can construct formally supersymmetry with respect to one supercharge and with respect to another supercharge and obtain so-called MN supersymmetry. And the simplest representation is called 1, 0 or 0, 1. We can combine them and obtain n equal 1, 1 gauge theory. This is just maximally extended supersymmetric gauge theory in 6 dimensions. Maximally extended in this sense that the maximal spin is equal 1. So it means there is a vector field in the multiplet. There are many relations between n equal 4 theory and 4-dimensional and n, 1 theory in 6 dimension. In both cases, we have maximally extended rigid supergauge theories. In both cases, the theories are anomaly free. In both cases, the theories can be formulated in terms of harmonic superspace. As to n, 1 theory, there are two supersymmetries. There is a manifest n, 0 supersymmetry and additional hidden 0, 1 supersymmetry, and together we have full 1, 1 supersymmetry. There is the same situation in 4-dimensional n equal 1 Soberon-Mills theory. There is a manifest n equal 2 supersymmetry and the additional hidden n equal 2 supersymmetry. Okay, so harmonic superspace. It was constructed firstly by Halperian, Ivanov, Kalitsyn, Ogivetsky, Sakachev in 1984 and 85, and there is a book where it is presented in the very convenient form, the book. And the general aim was, if in principle there is enough constraints, too many anti-commuting variables. But in harmonic superspace, there is a special procedure how to get the superfields, which are representation of n equal 2 superalgebra, and depends on the less number of anti-commuting variables. The number of anti-commuting variables correspond to n equal 1 supersymmetry. So it's, the theory becomes more or less simple. 6-dimensional approach to harmonic superspace was initiated by Haustel, West, Zupnik, and I will follow the recent paper Bassart, Ivanov, Smilga. Okay, so a little bit about this formulation. So we begin with Minkowski space coordinates, add some number of anti-commuting variables and some number of variables u plus minus, which are called the harmonics. In this space, it's possible to select some subspace with these coordinates, and this subspace is closed under the supersymmetry transformations, 1, 0 supersymmetry transformations. So in general, we have theta plus and theta minus as anti-commuting variables, but in harmonic analytic subspace of harmonic superspace, we use only theta plus. So the number of anti-commuting variables less than in general case. The field theory in harmonic superspace are described in terms of harmonic derivatives and some spinor derivatives. It doesn't matter for me is their concrete form, but only I would like to emphasize only that there are some specific objects. Okay, so there are two basic objects in n equal 1, 0 harmonic superspace, a hypermultiplet and vector multiplet. The hypermultiplet is described the analytic superfield Q plus, depending on analytic subspace coordinates. there is a equation of motion, there is an action. On shell, this theory describes the scalar, complex scalar field and spinor field. It's a hypermultiplied the superfield responsible for supersymmetric matter. Vector multiplied describes this analytic superfield V++. It contains in the shell vector and spinor, and there is a action for the theory. It looks like non-local, but non-locality also in harmonics. It's local in space-time. So since we work in high dimensions, we introduce the dimensional full coupling constant. It is a gauge theory. There are the gauge transformation, but it doesn't matter in principle. Okay, then we can couple superfield V vector multiplet with hypermultiplet and obtain the supersymmetric theory describing the interaction of vector multiplet with hypermultiplet. And if we take hypermultiplet in adjoint representation, in the same representation as a vector multiplet, we obtain n equal 1,1 supersymmetric theory. This is just a 1,1 supersymmetric theory. It formulated in n equal 1,0 harmonic superspace. There is manifest supersymmetry, and there is extra hidden supersymmetry. So there is a total n equal 1,1 supersymmetry. So then I will start to discuss quantum structure of this theory. First, how to calculate, how to organize calculations. I start with first one loop case. We consider harmonic superspace formulation for the theory. Then study effective action, which is basic object of quantum theory in general. There are two problems: how to formulate effective action in the most symmetric way, and how to organize calculations in the symmetric way. So first problem is solved in terms of background fields method. Background fields method is such a formulation of gauge theories where effective action is invariant under the classical gauge transformations. We know in general, gauge structure effective action is ruled by word identities, which in terms of Young-Mills theory, they are called the Slavnov-Taylor identities. But we can reformulate theory such a way that effective action is invariant under classical gauge transformation, and these word identities takes a very, very simple form. So then how to make calculations to preserve all symmetry? To do that, we use the so-called proper time technique or heat kernel technique, which also allowed to organize calculations with preserving all symmetries, both supersymmetry and gauge invariance. In principle, we can construct calculation in terms of Feynman diagrams in superspace. They are called the supergraphs. In this case, we have manifest supersymmetry, but no manifest gauge invariance. Then we consider n equal 1,0 vector multiplet coupled to hypermultiplet, and hypermultiplet is taken an arbitrary representation of gauge group and calculate divergences. But before, let me say some words about the background fields method. In this case, we split fields into two pieces: background field, quantum field, background field, quantum field, and in process of quantization, we impose gauge physics condition only on the quantum fields. And there are some specific cases how to do that, how to take the appropriate gauge physics condition. Situation a little bit analogous to what we done many years ago for dimensional equal to Sverre theory. Okay, sorry. Okay, but I need this consideration, and one loop effective function given this form, a trace logarithm of some differential operator acting in superspace. Then, in principle, we can develop the supergraph technique. There are the propagators and vertices, the basic feature of propagators is the appearance of Grassmann delta function here, Grassmann delta functions, which equals 0 when θ1 is equal to θ2. So then the structure of divergences can be studied with help of power accounting. You can calculate it. Superficial degree of divergences is L number of loops and Q number of external lines for hypermultiplet, and D is a number of D spinor covariant derivative action on lines. The possible form of counterchamp was found by Bassart, Ivanov, Smilga without quantum calculation on the basis of symmetries of the theory. In Vanhove, we have 3 terms in the divergent part of effective action. Then we study form of divergence on the basis of power decanting. It gives us that the power accounting predicts this term and this term, but this term is prohibited by power accounting, so there are no one-loop divergences of this form. So then calculations, for calculations we use the proper time technique. When the trace logarithm of the operator is represented in these forms, integral over proper time. Epsilon is a parameter of dimensional regularization is this scheme. O is one operator, X on delta function. The delta function contains Grassmann delta function, but O contains the derivative action on derivative over anticommutative variables, and non-zero result will be when all delta function is cubed. So this is the final result. So the result is given in terms of some Casimir operators, C2, T, TMN, CMN. It is for general 1,1 gauge theory. But in n equal 1,1 theory, all fields are taken in the same representation. Then all these terms equal 0. All the terms equal 0. And we obtain that the one-loop divergence is completely absent. It's theory one-loop free, one-loop finite. Theory is one-loop finite. About 2 loops. In this case, again, we use the background fields method first, then consider the power accounting and analyze the superficial degree of divergence. Then it was proved that the possible two-loop divergence must have the following form. So F plus plus is the left-hand side of equation, classical equation of motion vector multiplet, and some constant which diverges after removing regularization. So in two-loop case, there are 4 diagrams. Let me say, I work with background fields method. It means I consider only the vacuum diagrams, but all line depends on the background fields. Depends on the background field. Then one can prove that this diagram is finite. These are 2 diagrams cancel each other, and the only divergent diagram is equal to this one. So this is the final result for calculations. It just corresponds to power accounting. This is the coefficient. And some interesting point of this theory, there is only leading two-loop pole, but no subleading pole at all. We assume that the reason of that is in one-loop approximation theory is finite. So there are no divergent subdiagrams in the theory. And last point, how to include hypermultiplet. In principle, it can be calculated the same way, but there are some simple arguments to do that without calculations. So we start with this result, and impose a supersymmetry under the hidden transformations under the hidden transformation 0, 1, comma 1. Then instead of F++, we have E++, which is a total left-hand side of equations, classical equations of motion for the theory vector multiplet coupled to hypermultiplet. And we see first the two-loop divergences vanish on shell as we expected. And second, there is a very interesting observation. There are two contributions from the equations of motion. It means off shell we can make transformation of this field, the V++ field in the classical action this form, and cancel two-loop divergence at all. So let me summarize the results. So we considered n equal 1, 0 supersymmetric theory in 6th dimension. We developed background field method, which allows to calculate effective action manifestly gauge invariant and supersymmetric form. And we developed a technique how to extract one loop and two loop divergences. In one loop approximation for this theory, we see that there are no divergences at all. It is one loop finite theory. And in two loop, we calculated effective action in vector multiplet sector, in the hypermultiplet sector. So we see general understanding for n equal 1, 1 supersymmetric theories in 1 and 2 loops. Thank you. I stop there.
I know that you had a project of doing similar calculation in higher derivative renormalizable theory. I just wonder if there is recent progress in this direction.
Okay, so I wanted to include high derivative theory in the talk, but it demands some more time. So we considered with n equal 1, n high derivative theory. Grosjean was given in your paper with Evgeny and Zupnik. And again, constructed background field method and technique for calculations. And we have one loop counter term in completely supersymmetric engaged invariant form. The theory with dimensionless coupling constant. It's similar to, I don't know, high derivative gravity, for example. It's an interesting point. We found that since the theory is high derivatives, there is no reason to fix the sign as action. In conventional theory, the sign is fixed by a condition of positiveness of energy, but here the energy is not positive. In any case, so there can be different sign as the action. Then, if you calculate beta function, we can take the sign corresponding to asymptotical freedom. But another choice of sign will be no zero problem.
But have you just found the coefficient? Because I didn't follow.
No, I have no. It is here.
Yes, here you don't have. But
we have coefficient in the paper.
You have coefficient in the paper, and it coincides with
component
calculations,
yes,
right?
Yes.
Okay, thank you. I just didn't follow.
Yeah, with your calculation, the safety calculation.
Yeah, maybe that's not a question to you, but I mean, there are many experts in preservative calculations. I'm very much surprised that at two loop you have just 1 over epsilon squared. At one loop, you have no divergences whatsoever, and in two loops, you have 1 over epsilon squared. This is very strange. It's very peculiar situation. Normally, it's the opposite. Normally, if you have no divergences at one loop level, then you have 1 over epsilon in the second.
The only divergent diagram it looks like this. It's contained like a product of one loop diagrams. But in one loop case, you have 1 over epsilon. So it's 1
No,
over.
no, but one loop you said it doesn't have 1 over
No,
epsilon.
no, we have no divergence when we take into account all fields. The hypermultiplet, the vector multiplet, here only part of fields, only vector multiplet contribution. So there is no.
Yeah, but the complete divergence in complete theory is 1 over epsilon squared. Is that correct?
Sorry.
The divergence in the complete theory with all fields taken into account is 1 over epsilon squared.
Yes.
Is that correct?
Yeah.
At two-loop level.
Yes.
And no divergences yet at one loop. That's very peculiar.
It can be destroyed. Maybe the another gauge fixing condition.
But you have somewhere mass term.
Oh, mass term. So maybe you are right.
There is some power mu squared over something.
Yes, it seems you are right.
When you expand, you have log.
It seems you are right. When we consider mass,
is one loop divergence.
I believe if you consider mass, it can be destroyed completely. In massive case, destroyed completely. It's strange, but I let me start from the very beginning. How what I said. Just a minute. So what I would like to emphasize, there are some wonders of the extended symmetry. So I understand your question, but its result was completely correct.
My guess, I don't know. My guess is that probably what you found is a specific of a non-renormalizable theory. This one of the epsilon squared term, because you have an experience with renormalizable theories. And this theory, 6-dimensional, is not renormalizable. And maybe that's my guess, I don't know, is that's the reason of this peculiarity. I don't know.
Maybe. My point of view is the reason is absence of subdiagram divergences. Жень.
Okay.
Well, the beta functions, no beta functions here. Yes.
Can you clarify once more? Whether may you clarify once more? Whether only one side shown with dot give 1 divided by epsilon square direction. And does it mean that other diagrams you draw have 0 or no?
Yeah, let me say.
Let's have a look diagram by diagram.
Let me say. This diagram is finite at all. And two zero diagram cancel each other because the hypermultiplet and the host in the same representation, but opposite Erasmus parity.
And only G1 is given.
Only this diagram gives result.
No subdivergence?
No subdivergence because it's finite theory in one loop. No, this is the point. It's a specific of this theory. There are no one loop divergences.
So it is you claim that this diversion as itself as
yes.
1 divided
yes. Yes. Yes.
And no 1 divided
yes. This is correct. This is correct.
And so that's in other way that you claim that this diagram, if you think in terms of higher derivative regularization, then this diagram will be log square, some lambda q square, and no log terms.
So it seems something like this. But it may be interesting to consider this diagram as a high derivative regularization. Maybe it's interesting. I will ask Kostya to try it. Yeah.
Thank you.
Unfortunately, we have more to continue our discussion. Okay.
Hello.
So Pierre, you can start.
I can start. Okay.
Yeah.
So thank you very much for the invitation to give this talk. And first, I want to congratulate all my colleagues. I mean, who have this anniversary from Dubna. I mean, I wish I could be present, but I'm not present, unfortunately. So, but I hope there will be many more occasions for, I mean, meeting them and working with them. So I will talk about some work that I've been doing over the many years with Émile Biombo, Paul Damgard, and Ludovic Planté, which is to compute the post-Minkowskian expansion in for two-body gravitational scattering. And we are interested into the classical scattering, which is then with the aim of computing something for the gravitational wave physics and classical observables, but we are doing it using quantum scattering amplitude. And the reason is that if you think that there is something beyond, Einstein gravity, that Einstein gravity is part of a low energy effective action, that it can contain either extra field or extra field or extra derivative correction from whatever UV completion you like. You want to be able to understand what are the effect of this possible correction to, for example, the gravitational wave signal. And in fact, thanks to a long list of people, but essentially from the scattering amplitude community, now there is a new way to evaluate, as I said, this classical observable in gravity, starting with computations in a scattering amplitude. So you do quantum scattering amplitude, and there is a way to extract classical quantities that then you will feed into this gravitational wave physics. And the point of the talk is to explain to you some of the techniques we have developed for that. And I want to say it's very exciting because it allows you to compute. So here the action is written in 4 dimensions, but then it works as well in higher dimensions. So if you think that you want to probe gravity behaves in higher dimension, the formalism I'm going to explain works as well, very well in higher dimensions. Or, as I said, if you have any correction, you can feed it into the amplitude framework. So one of the new insights is actually, if you look at the two-body scattering, you have an S matrix. You would do so this is the energy and this is the momentum transfer, and you do a perturbative expansion. Okay, so here it's only purely gravitational interaction. So the coupling constant is G Newton, and L is the number of loops. And traditionally, you would think that each loop order is suppressed by a power of h bar. But this is not true, actually. What's happening is that at each loop order, if you take h bar to 0, and you scale the momentum transfer by 1 over h bar, you work with the wave number. What's happening is that at each loop order, you get a piece that is 1 over h bar times, some power of the momentum transfer that depends on the dimension. And here there is some coefficient that depends on the energy and the momentum transfer. So the thing is that this is, I mean, in a sense, I mean, when you think about it, this diagram that I've written here, where you have two massive particles with momentum, mass, and spin, when they scatter gravitationally, you can draw this graph with no h-bar. I mean, you solve perturbatively Einstein's equation, you invert the Green function, and then there is no h-bar. But you can say, well, maybe I want to see this thing with quantized field. So I'm quantizing the lines here. I mean, this is my scattering. I'm quantizing my graviton, my massless field. And so there are h-bar everywhere. But then at the end of the day, I should recover this classical graph from my L-loop scattering amplitude. And indeed, if you take an appropriate limit, I mean, you can extract it. And what you see here is that in this Laurent expansion, so when you do the Laurent expansion in h-bar of your scattering amplitude, you see that the term you want to compute, which is the classical one, is getting deep and deep. So there are a lot of terms that are more singular. That seems strange than the classical term. So all the terms that behaves like positive power of h-bar are called quantum. The one I want is this one, but then there are a lot of terms that are more singular when h-bar goes to 0. In fact, they are needed, I mean, for the unitarity of the S matrix. But when I'm going to tell you how you can treat that. So the thing is that what you do is that the logic is that you are in a scattering regime. So you scatter two body, you extract, for example, a scattering angle. From this, you can reconstruct an effective potential, and then you do analytic continuation and you go to the bound state problem. Okay, so it's the standard analytic continuation. So from a scattering amplitude point of view, the natural object to look at is a scattering angle. So the scattering angle, you get it by you Fourier transform your scattering amplitude with respect to the momentum transfer, and there's B here. And then in that space, you want to exponentiate. And I want to exponentiate in a way that here I'm getting just a classical quantity. So all the h-bar is here. There's no h-bar in my purple delta. And the big delta here contains everything that I call quantum. But from this, I use the standard saddle point. I can extract by varying this guy respect to B, the sign of the scattering angle. Okay. Now, as I said, the thing is that you see why I need all these higher powers of h-bar here. Because when you expand the exponential, you just have, because of the property of the exponential, you get 1 plus delta over h-bar plus delta square over h-bar square. So you need to have a lot of 1 over h-bar terms that are needed to rebuild your exponentiation. So you have to iconolize correctly your amplitude. And so all these guys here are exactly needed to get this proper 1 over h-bar in the exponential. So now there's a question of efficiency, because you want to go to know the frontier is 3 loops, 4 loops, and pure gravity. So you want to extract in an efficient way the thing that you are interested in, the classical part. And this part, which essentially you don't need because they are part of the lower terms that are needed for the exponentiation, maybe you would like to not having to compute them, because this is not really, it's good for consistency of the computation, but it's not really what you need. So in a sense, that led us to rethink about what is actually the exponentiation of the S matrix. So as an operator, the S matrix is the identity and the scattering matrix, but then you can write it in terms of the exponential of an operator we call n divided by h-bar. So of course, the unitarity of the S matrix imposes some reality conditions on the eigenvalues of this operator, fine. But you have to tell as well what is the completeness relation. So what is 1? So 1 is, it's a two-body scattering. So in the phase space integral, you have your standard phase space integral over the momenta of your two-body scattering, so your massive matter, but you have as well an infinite sum of virtual gravitons that you can exchange. So these guys are virtual gravitons. So if you write it, for example, the unitarity relation at two loop, you get the thing that is the usual, okay, so I'll show the graph, the two particle cut, where you have here a one loop and a tree, and you exchange just your massive matter. So here I have already used the iterations that expresses the one loop in terms of the iteration of the tree. So this is just the cut. And then, but at this order, you can exchange as well a virtual graviton in the middle. So this is this one. So here there's a virtual graviton. And to all higher loops, then you get more and more exchange. You can exchange more virtual graviton in the middle. And the thing is that this whole process is unitary. So if you, for example, just decide to compute some subpart of this, then the modulus of your S matrix will be smaller than 1. So it's not B1. It's not, but okay, so I will come back to this contribution in a minute. Okay, so then, okay, so this is standard unitarity. But what I want is I want to do a small Q-square expansion. So I want to have a small, I want that this is my massive line, and I want that the exchange of my momentum transfer is small. So in a sense, I want that the energy of the lines varies slowly in my process. So let me see. So in a sense, there's some limit of the unitarity cut that we call the velocity cut. So let's see what happens if you have a box and a cross box. So first, consider the scalar one. So the sum of a scalar box and a cross box, because it's all symmetrical, it takes this nice factorized form, P1, P1 prime, P2, P2 prime. Oh, I'm sorry, that should be a M2 here. And P2 square is M2 square, P2 prime square, I'm sorry, this is M2 square. And so the masses are like that. So what you do is that you shift by the momentum transfer, and I neglect the term in L square in the denominators here, because when you do this small momentum transfer expansion, the L square will essentially cancel the L square, will give you tadpoles, and the tadpoles will never contribute to the classical result. Okay, so you do that, you do a small H bar expansion here, and then you see that you have an expression that is essentially, that is in each parenthesis 1 over x plus I epsilon plus 1 over x, minus, I'm sorry, that should be a minus, 1 over x minus I epsilon, and that is a delta function. So you use the principal part prescription, yeah, and because there is a minus and the signs of the epsilon is the correct one, then you get that these things are delta functions. And so if you do an expansion in the small momentum transfer, then you get a piece that has 2 delta function and a piece that has 1 delta function. And there's a power of the momentum transfer, and there's a power of H bar here. That is just the classical bit I want to get. Of course, there are other terms because I'm doing an H bar expansion, but they're not contributing to the classical part. So that means in general, the way to use this unitarity and doing this small H bar expansion is essentially to convert the unitarity cut to this delta function insertion in your loop amplitude. So at one loop, in the full gravity, you get this structure times coefficient that come from the fact that it's pure gravity. And these integrals, you can compute them. You have 2 delta functions, you are in d dimensions, okay, you compute these integrals. And actually, if you are in 4 minus 2 epsilon, this integral is going to give you something that is related to the square of the tree. And this integral is going to give you something that will come as the one loop correction to my iconal phase. So then I have this expansion, then I see the terms that are in this expansion. The fact that this guy is a square is because the tree contribution to the iconal phase here came with a square, and all the factors have to work properly. Okay. So now if I do that at 2 loops, which is essentially the drawing I have here, okay. Then I have 4 delta functions, which when I compute it, then I get the cube of the trees. Then I have the sum of two delta function, which give me the tree times the classical part of one loop. So that means this is going to be the cross term when I do the expansion of my exponential here. And then there's a bit that is two delta functions again, but of different distribution of the argument that will give me the two loop classical contribution to the diagonal phase plus a tree level contribution times the one loop quantum. So this is the big delta that I have here. So I'm saying that I don't want to exponentiate everything. I want to have the exponentiation of the classical part, and I keep the quantum corrections as a prefactor, okay? So if you do that, then you can reorganize completely your perturbation. And just, for example, here you have your two-loop diagram like that. So what happens is that you know that what's going by these rules I described with the delta function, you know that this is what's going to contribute to the exponential. So you just have to look at the same graph, you put the delta function at the appropriate place and you compute them. And everything else that you throw away either contributes to the thing that is needed for exponentiation or to quantum part. So that way, that makes a very, very simple rule for zooming from quantum scattering amplitude that is very, I mean, you know, you can imagine I'm doing pure gravity, right? I'm thinking about pure gravity, two loop in d dimensions, or pure gravity, three loops with massive matter and a change of gravitons. I mean, the expression is huge, right? So in a sense, I mean, it's, you would say there is no hope to be able to do the computation. Yes, you can, because now you have this way to think about how to zoom and approximate your integrand in an appropriate way and put these delta functions. So now the problem is different now. The problem is that you need to compute integrals that are not the standard one. You need to compute integrals that are, for example, propagators, like at two loops. So this is my a typical two-loop integral with various powers of the propagators. But then you have this delta function insertion. And so you can ask, I mean, how to do this evaluation. So what you do is that you can perform there are two delta functions, you perform two integrations. So then you reduce your d-dimensional integral to a d-1 integral. So this part is unchanged normally, okay? And now what you get is that you get something that is a propagator, but the propagator is not a standard one. So he has this deformation this is the energy of your two-body problem. And then there is the K is some momentum that is a combination of the incoming two incoming momenta. So you need to compute these integrals. So what happens is that this type of integrals, I mean, the family of integrals, all the integrals you meet in that form, I mean, you can do actually the tensor reduction using little red by Raman-Lee. And to the surprise is that for the pure gravity computation at two loop, you only need to compute 9 master integrals. So the 9 master integrals is some specific choice of the integers here that I have here, and the integers. But the thing is that I just want to show you what is the matrix for the system. So the derivative of this, so there are many more master integrals you can find, but the one that contributes to the classical part, there is a subsystem that is 9 by 9. And the derivative of this set of masters with respect to the energy is this matrix that depends on the energy of, and there's an epsilon here. So it's even in you can present it in a nice form, which is the epsilon form that I suppose Roman in his talk will explain how we integrate this sort of system. So you need to integrate that. So for example, let me look at this integral that is an interesting one. So this is an integral that is known 3 minus 2 epsilon because I have done my 2 delta function integral. And there is this modified propagator here. It satisfies the differential equation that is this one. it's one of the, it's in the list here, okay. Which, so you solve it, then you solve it, gamma square minus 1 to the power epsilon, and then this is a constant of integration. So here, essentially, because only have infrared problems, not UV, I'm thinking that epsilon is negative, okay. So when gamma goes to, yes, okay, so, but, yes, so when gamma square goes to 1, that means the static limit, that doesn't blow up. I mean, because epsilon is negative, this will go to 0. So if you do, you can perform an explicit evaluation of this integral using standard techniques, and you find that the epsilon expansion of this function is this. Okay, so you recognize the same power here, and this expression tells you what is the constant of integration. But suppose you want to do a static, so a small velocity, small energy expansion. So when gamma is close to 1, this is like the static case, and you want to expand in the region of the integral where this part is small compared to that. So which is actually what this is the so-called potential region that has been studied in many papers by Zwiebern and their collaborators. When you do that, then you realize that you get tadpoles integral at each step, and the integral, when you do the integration, then you get 0. So another way to say that is that it's setting the boundary conditions of this integral so that the constant of integration is 0 in that region. So there is a region you can decide to focus on the part when where the constant of integration is 0. That means you miss, so you don't have this type of integral. But if you look where that integral contribution comes from, it comes from contributions that actually are needed when you go to a very high energy. So in a sense, you can truncate, if you want, your system of differential equation and set some masters to 0, but that doesn't allow you to give the full answer. So if you can separate, in fact, your computation in two pieces that are the so-called conservative part. So the scattering angle for the conservative part, this is the tree, this is the one loop, and this is the full two loop expression. But so that means is the part where, for example, this that doesn't receive contribution for these integrals. I mean, there are other integrals like that doesn't contribute to that conservative part. But if you look at the high energy behavior of that quantity when gamma goes to infinity, I mean, it is incompatible with the high energy behavior you can compute using the formalism of Amati, Ciafaloni, and Veneziano for what we know about the very high energy behavior of gravitational scattering. So because indeed there is an extra piece, so the full answer is that conservative plus the radiation reaction part, the sum of the two, and it contains actually a piece that is as well as some logarithmic divergence when gamma goes to infinity that compensates for the bad one and leaves you exactly what you need for the ultra-relativistic regime, and it matches the direct the result you can do by having this direct ACV type of argument. But what I say is that from the unitarity argument I gave at the beginning is that these two contributions as well are needed because of the unitarity of the computation. So you have a computation where you have both the conservative part plus the radiation reaction. So and this is where you have this exponentiation of the unitarity F matrix in a way. So in a sense, I mean, this is the way we are now performing the computations, and what we see is that actually, although pure gravity seems to be very complicated, there is a way to simplify the computations, to go to just zoom on what we need with a clear physical interpretation, and as well in the argument. So far, in what I've discussed, we only looked at the pure gravity case, Okay, we have as well done the computation in the supergravity case, maximal supergravity. But it turns that in the maximal supergravity case, there's the same number of mass stars. For some reason, up to two loop, the two computation is not much simpler to do maximal supergravity. The only thing that changes are the coefficient. Yeah, so maximal supergravity doesn't have the -1, and this coefficient changes as well. But you can apply it if you want, if you like, modified gravity scenarios. Do the same. You can include your extra couplings, higher derivative couplings, or coupling to some overfield, I mean, scalar tensor theory if you want. Do the scattering amplitude, extract the classical limit using this, and then get your classical observables and try to compare with signals in gravitational wave if you want. Or you can do it in higher dimension and try to see if there's something funny, because gravity is richer in higher dimensions, some interesting aspect of gravity happens there, and then you can apply that, and there's nothing that stop you from doing that. Okay, so this is all I'm going to say today. We have in the probe limit, just to make an advertisement, in the probe limit, we are finishing the 5-loop computation, so that will be soon in D dimension. So that will be soon published, I hope, maybe before the end of the year. So this is to tell you how efficient we can be now. Thank you very much.
Thank you very much.
Field theory methods are the classical contributions for gravity wave detectors. This is social request for that calculations.
So,
right? Similar. Can you hear me?
Yes. Yeah. Can you speak?
That methods, contemporary field theory methods calculation is asked for the gravity wave detectors.
Yes.
Precisions, right? So,
okay.
Similar thing is for modest detectors like Cherenkov detectors. We can calculate by quantum field theory methods, quantum electrodynamics, the Cherenkov radiations, and it's a simpler than classical approach to. This is common. Thank you.
Okay, so maybe I don't know, but the thing is that, yes, the focus was more to simplify the physics. I mean, how to. Okay, so in a sense, so far, I mean, the gravitational wave experiment, they don't see deviation from Einstein gravity, but ultimately you want. I mean, you think that ancient gravity is not the answer. And the thing is that if you apply, I mean, it's good to be able to have method that allows you to test any phenomenological model you want, okay? And the thing is that gravity seems to be very difficult, but I mean, under the impulsion of the scattering amplitude community, and there are many people who contributed to that. I could not do justice to everybody. We have found many simplifying statements that makes the physics more clear. So I think this is, with the development of the gravitational wave physics, I think it's very, I mean, it's a very needed point of research. Yes. Any questions?
Please. Pierre?
Yes, hello.
Thank you. When you go to higher orders, to fifth order, do you encounter sort of analytical problems by being in 3 dimensions, which we avoid in 4 dimensions? And are you in need of expertise?
Okay, so so the thing is that so far, yeah, okay, that's a good point. You're asking about the complication in evaluating the integrals, right?
In three dimensions.
Yes, in 3 dimensions. So far, what's happening is that we could purge the computation in the so-called probe limit when one mass is much bigger than the over one. Okay. And then you know that you are going to reproduce a Schwarzschild type metric. And the only integral you meet, they give you, they evaluate to some simple rational numbers. I mean, so there's nothing complicated there because of this probe limit. In general, what you are going to get when you go to so here this computation is a two-loop computation. When you get to free loop, in the full gravity case with no approximation, you get some elliptic type of integrals that you meet. And so you expect indeed that you are going to get more and more complicated quantities that it's not even clear if I will be able to express them in terms of some elementary functions. So that I don't know. But the thing that is that you have to remember is that this from this angle, I'm going to reconstruct. I mean, so this is another talk. But what we do from this angle, we reconstruct an effective Hamiltonian, which is an Hamiltonian from which, if you use the standard Hamilton-Jacobi equation, you can compute the scattering angle. So you follow Landau-Lifshitz and you know how to do that. So in a sense, I mean, what are the functions that you can expect in this classical gravitational physics for this Hamiltonian, for the effective potential? I don't know. I mean, I would be surprised to meet a very exotic function, but I don't know. I mean, I have no idea what's going to happen there. But in the probe limit, we so far have not yet met any difficult integrals.
Yes, but you're interested in eventually in the collisions of black holes of comparable masses.
Yes. But in principle, yes. But the thing is that so far, doing the comparable mass at free loop is under the way. But in the probe limit, when one is much bigger than the other one, we could to higher order because things simplify. So this is where we are. But I know, I mean, I agree, but I don't know what to expect in a sense. I mean, but there are some elliptic integrals that comes already at free loop. That for sure. It's already in the papers by Zwibern, they mentioned that, that integrals.
Thank you.
I didn't get it, Pierre.
Yes.
I didn't get it. You're getting radiation.
Yes.
Well, what you calculate is basically 2 amplitude, right?
Yes.
So it's a exclusive amplitude, not inclusive amplitude, right?
Yes.
So how do you get radiation from exclusive amplitude, 2 scattering?
No. Okay, so that's an excellent point. Okay, I mean, sorry. So the thing is that it's a 2-2-2. So this is really, you really have to look. So first you have to look at my completeness relation, right? Okay. So here, this graph is 2-2-2, right? I don't radiate anything, but I have here an intermediate graviton. If you cut it here, if you cut that line, then of course you emit a graviton. So what's going to happen is that this is precisely the point. So what I'm doing is that I'm in a scattering process when it's conservative, right? But I want to use that to compute, to extract an effective Hamiltonian and then go to the regime where I have the bond state problem that emits gravitational waves, because I want to have radiation of gravitational waves. I want to have a system that loses energy. So the thing is that the loss of energy. So in a sense, I mean, it depends the way you think about it. So either you think that you have in that context, you see this graph as being a graph where you have emitted a graviton and then you have reblued it to make it this complete 2-2-2 scattering, or you want to cut that graph in the middle and see that there is something that is like emitting a graviton. And these contributions like that, I can have as well have, if you want, graviton lines that will go like differently. They are in correspondence with what the people call the radiation reaction. Where did I write that word? Yes, the radiation reaction. And the radiation reaction are precisely these things that are linked to the loss of energy momentum in the collisions. So there is indeed, from my computation, the information about the way you lose the energy when you go to after you go to the bond state problem and you do the coalescence. But in a sense, I mean, what is interesting in that computation is that everything is contained in this S matrix. And if you don't include this radiation reaction term, you are not getting the right high energy limit. Or another way to say that is that in the full loop computation done by Zwiman and their collaborator, the potential they give for the classical scattering, because they set the boundary conditions in the way I described here. They have a potential that has a 1/epsilon divergence. And they could identify that actually the diverging part in their potential is actually due to this radiation effect. Okay. But if you do the computation in the correct, I mean, when you include everything, you set the boundary condition differently in what we call the soft region, then the answer has no divergences. The effective potential is finite, but it contains effect that you will need to interpret as radiation when you go to the bond state problem. So there is here a question on which I'm not totally sure yet how to treat that totally. I mean, but that's a fact. I mean, that's a fact that if you want to reconcile the 2-2-2 scattering, the high energy behavior, and the fact that you want to have something that is a finite effective potential, you need to include this virtual graviton exchange that, if you look at what the unitarity gives you, are exactly the radiation at the previous loop order. So that's the way the amplitude computation is consistent. But in a sense, I mean, there is some interpretation that you need to be clarified really on the connection to what really people call the radiation in that case, yes, in pure gravity.
Okay, more questions? If no questions. Thank you very much.
Thank you.